Welcome back, everybody. Today we're going to talk about water to air. This is a known subject that is not much known about it in our industry. I want to bring some clarity on this subject. I don't want anybody to be concerned or scared that they can't work on it. If you can work on air to air, heat pump, or straight cools, you can definitely work on a geothermal water to air piece of equipment. And so I hope this video helps you out. Stay tuned. Okay, getting right into it here. Got a water to air diagram behind me. I'm going to go over the components in this diagram so everybody can follow along afterwards. We have the unit itself with the top of it being the blower section and the bottom of it being the condenser section. On the top section you have your expansion valve, your vapor line, your evaporator coil. You have your liquid line, which is the purple line here. We have our blower itself, direct drive motor, so air is coming in across through the coil. You got a return duct bringing that warm air across that coil, feeding that supply air throughout the forced duct system. Below down here in the condenser section, pretty easy. You got a compressor. It's a heat pump, so we have a reversing valve, right? You got our three chamber valve here where our discharge comes in. We actually are sending it this way to the left, which is going into the condenser coil, also known as a water jacket. That condenser coil's got that hot discharge gas going through there. And as that water from the well pump at 71 degrees Fahrenheit consistently never changes up or down, as it runs through this water jacket in its section, it's actually cooling down that gas where that gas is condensing to a liquid. Bypassing the metering device to be metered up here at a high pressure liquid and allow that liquid to feed our evaporator coil. Now the condenser coil, I'm going to go off screen for a second. I'm actually going to hold one up so you can see it. Okay, and I'm also going to hold up a familiar coil, just used to. This is a portion of a condenser coil on an air-to-air unit. You see your piping here. Those are your liquid line, or sorry, your discharge gas line that is allowing that gas to condense based off the fin plates that are cooling down because of the air moving through there, rejecting the heat off of that copper piping, condensing that gas down to a liquid. And so the air and the refrigerant do not mix. They're in, the refrigerant is a sealed circuit, it's its own refrigerant circuit, right? So they, just like the air doesn't mix with the refrigerant here in the water jacket or the condenser coil, we have our refrigerant coming in, and as it comes in through the coil and it runs through this coil, it's coming out as a liquid, right? And the water, as the water comes through, I'm going to go ahead and just see if we can see this on camera here. You know, you have two different circuits in there. There's a water circuit, and then we have a refrigerant circuit. So the water is actually not making contact with the refrigerant. It's just moving around it, and it's allowing that hot gas to cool down and condense. This is also the evaporator coil when it's in heat mode. So it will sweat on the outside as humidity will collect on it and it will condensate, right? And so that's the water jacket that we're talking about. And, you know, that's 71 degrees. That never changes because it's coming out of the ground. It's coming out of a deep well, and that water is not warming up from the point of the aqueduct, that aqueduct that is allowing that water to be present, you know, as long as the well's not dry. That water is coming through there at a consistent temperature. So whereas in air-to-air units and air-to-air straight cools or air-to-air heat pumps, we have a SEER rating, seasonal energy efficiency ratio, and that number changes based off of the outdoor ambient temperature. The warmer it gets, the lower the efficiency, the higher the amp draw in the compressor. It's the gas that it's pushing is at a higher pressure. And as that temperature starts to drop, the amp draw starts to drop on that compressor, so you wind up moving that gas more efficiently through the system. Therefore, we can't say it's one efficiency, that efficiency changes throughout the day and throughout the season, throughout the year. Whereas water to air, we work on EER, energy efficiency ratio. There is no seasonal part because it's 71 degrees year round and all day long, no matter what the outside ambient temperature is, whether the outdoor ambient temperature is low or it's high. This water is always a consistent temperature, which makes these far more efficient than air to airs. A lot of these units are commonly misdiagnosed, and people don't see them a lot, and they wind up replacing them and converting them over to air heat pumps and whatnot with refrigerant lines. And I just think that's not a good deal for most customers that have had these for a while. And at the end of the day, you know, if you're trying to sell them on efficiency, there's not another unit on the market that's going to be more efficient other than a geothermal water to air. And these things come as single speed, 2-speed, and variable speed blower applications, so they can actually target comfort better than you think, and you know, they can get over 30 EER in efficiency. Back to the water jacket itself, I have this in cool mode. You can tell because I have this red and this blue. Let's just go back to that reversing valve. We're moving the gas to the left side of this valve into here, and as we come back at a low pressure gas, it's moving back through the valve and into the inlet of the compressor. Now, what brings this system on is a thermostat. It's going to give a G call for your fan to come on, a Y call for the contactor to pull in, and an O call for the valve to energize and cooling. There's no heat strips here, and at the end of the day, you know, it's pretty simple, pretty basic stuff. There is a external low voltage wire that does need to go out to the water valve, which is 24 volts. That valve is normally closed. It takes voltage to open it up. When it opens up, it will allow water to come through the jacket and move through the system. So I have a well pump on one side that's working off of pressure, and once that pressure is achieved, the well pump shuts off. It's going to quickly hit pressure the moment this valve closes, right? And so when we have a Y call to bring on the compressor and the blower and all that, when that comes on for cool, we have to have water moving through this jacket. So this valve has got to be open. So we have to send 24 volts on that Y call out here so that valve can open when the contactor pulls in. At that point, the pressure will fall on the well pump, engaging the points on the well pump contactor, which will bring the well pump on to help pull more water out of the ground. Now, you can have this on a deep well where it's artesian, and you may get naturally 3 gallons of water a minute, but 3 gallons of water a minute is only going to be good for about 1.5 tons. So if you have more than a 1.5 ton water to air unit, you're going to need, even if I had an artesian well at a 1.5 ton, I would still put a pump on it to make sure I was regulating enough pressure to get enough water out of that ground and get that consistent GPM, just because things do happen. The most common problem that we have with water and air units is actually there's no water. So pumps go out, breakers trip on the pumps overheat. There's problems with the wells going bad. We have water valves that can just fail, and remember, it's in a closed position, so if it fails, it's closed. So it's not open. So if it were to fail in the open position, then at least you would have air conditioning. You would just have a flooded out yard with all the water. However, you can even still you know, limp along a little bit until you replace these valves. We get a lot of scale that builds up in inside the coil, just because the water it's very hard coming out of the ground. So you know, there's a lot of minerals and stuff. Those minerals will cause some scaling on the inside. The moment you start scaling up on the inside of that coil, you don't get that heat transfer, because there's now a built-up layer between water flow and refrigerant flow, and they're in parallel with each other. So I got refrigerant flowing one way, I got water flowing in a direction, and it's the metal it's the copper, aluminum alloy, whatever the metal is, copper nickel plated, whatever they got going on inside there, their technology, their patented technology to allow positive heat transfer. If there's any scale built up, you just reduce the efficiency because we're not going to be able to condense very well. And so a lot of times these things do have that issue, but that's not contributed for the equipment being a problem. That's contributed from the well and the minerals that are in the well. There's filtration and stuff that you can put on there, but then you're adding one more layer of problems once those filters start to get restricted from those minerals. So you got to really stay on top of the maintenance on these. Now, if you have a good deep well and your water's being, is pretty clean, most likely you're not going to have a problem for a very long time. Typically, when we see these issues, they're not on deep wells, they're on shallow wells, right? Dirty evaporator coils, it's very difficult to get in there and clean these coils. A lot of times these things are installed and there's not a whole lot of access in there as you slide your filters in and out of there. It's about all the space you really have to get in there and actually clean it. So there's those issues. And then there can always be a refrigerant issue to where, something's going on here mechanically. Mechanically meaning I got valves that may not work. I got expansion valves that may not work, blowers that can go out, capacitors that can fail, contactors that can get pitted, compressors that can lock up. There's a bunch of things that can go on there. Technicians don't know what they're looking at. So if we had to say what is another problem, I have to put that up there because it is so common for a technician to walk up to this thing and they go, "What is that? What is that?" They have no clue. More than that, let's just go to the outside. This is part of it. You got to have a pump. A lot of them do not know what that is for, okay? And so there's a lot that we're going to cover here. Let's go into that well. As that well goes deep into the earth and we're pulling up that water when that pump is coming on because of that motor, right, turning that pump, we're going to extract that 71 degrees of water. We're going to go across a check valve. That way, when this is off, water doesn't fall back below the ground and then you have to reprime it. So that check valve is there to help that. So when this pump comes on, it's grabbing a hold of water immediately and it's pulling that water in. So it's not going to have an easy time doing that if it's just air, that it's moving. So it has to have water here in this area. So you want to make sure that that check valve is there. The pressure gauge, typically they run around 40 psi, and they have to be adjusted so the pump does not short cycle. Where it's pulling, if short cycle would be the pump is pulling too much water too fast, satisfying the pressure, and it's shutting the pump off. The moment that motor turns off because it's satisfied, if there's still a Y call, if there's still a demand on the actual, water valve, it's still open, causing that pressure drop. If the entire time that water valve is open, causing that pressure drop, you actually want to make sure that your pump is running the entire time. The pump should not turn off until that valve closes. So you want to regulate the pressure cutout on your well pump so it can run and not cut off, right? And so you want to make sure that thing is running and pulling water out of the ground the entire time you're getting a Y call. But the moment you lose that Y call and that valve winds up turning off, that 24-volt water valve, when it closes, that water comes in and it just stops. So therefore, you're going to quickly satisfy the pressure on that pump, and it's going to cut off because it reached 40 psi. You may have a bladder tank with some air in it just to help regulate and keep that pressure. Helps prevent that short cycle on that pump. As you can see here, everything in blue is where there's going to be water present. I didn't draw this going into the building, just to let you know that this is supplying the water to the actual equipment itself. And then I have a hose bib over here before I go to my unit. Why would I have a hose bib there before I go to my unit? Because I want to make sure I have proper GPM coming out of the well. If you don't have that and you're only working with a hose bib on the opposite side of the unit, meaning the exit part, then that you got to have that too. But in a lot of cases where we don't have this, we're diagnosing it from here. So if you're going to diagnose water to air, you want to be able to diagnose the GPM before the unit and after the unit. For example, If my GPM has not changed and I have the proper flow before the unit and I have the proper flow after the unit, but my head pressure is super high and I'm not getting subcooling off of that condenser coil, then there's obviously scale built up, right? So you would diagnose that the same way you would diagnose a corroded condenser coil on an air-to-air out of the beaches, right? You have plenty of airflow, there's nothing obstructing the air. However, there's no state change of vapor to liquid, and you're not rejecting enough heat off of it to condense because there's this salt and corrosion and all that built up on those coils. So it's the same concept on a geothermal water to air. And so you need these here, because not really for the pump, because this isn't supposed to be really used for everything else in the house and the yard as well. You really don't need to use this for irrigation, because the way we have it set up, you're going to be using it for irrigation every time the air conditioner comes on and runs, right? But in the event that there is a water demand, because you're using one pump, and that's for showers, that's for washing machines, dishwashers, cooking, and you're using it for your air conditioner, then at the end of the day, you may not have the proper GPM going to your unit. We're going to talk about that GPM real quick. This is be the exit. This garden hose is coming out. I have 2 gallons of water per minute per ton, which is 12,000 BTUs, which would be 1 ton. So example, if I had a 3.5 ton water to air unit and I need 2 gallons of water per minute for that 42,000 BTU unit to operate, then I need to be able to test that I have 7 gallons of water per minute. I'm going to go real quick and show you that with a field exercise that we did, where we filled up a 5-gallon bucket with a timer on it, so you can actually see that. So stay tuned to watch that real quick. All right, everybody, we just put the water to air unit in. We want to go ahead and show you the first thing you want to do is make sure that you're getting 5 gallons of water a minute. We're going to go ahead and demonstrate this by putting a 5-gallon Home Depot bucket underneath there, and we have a timer that we're going to go ahead and start. There we go. And what we're looking for is 5 gallons of water to be done in about 40 seconds, I believe it was, 43 seconds, because we need 7 gallons of water a minute on this thing. So we're almost full here on this 5-gallon bucket, and it's been right at 30 seconds. So we can safely say that in a minute I got 10 gallons of water. All right. Let's go ahead and set it back up on the well. All right, so we're actually not dumping the water right here. This is just a way for us to test it or run a garden hose off of it. So we're actually discharging back into the ground into a well. So we're going to go ahead and go on the inside and show you what the water to air unit looks like installed. This was drywalled in, so we had to cut the drywall out and get the old unit out. All right, this is the hallway. We've already boxed out the closet. So now that we've done seen how we take a bucket and we can put it underneath the hose bib and just crank it up and let that water flow, filling that bucket up and keeping track of that time, we're able to see that that bucket was able to be filled up in about 30 seconds, which is a 5-gallon bucket. And if we did the math, basically we would be producing enough GPM to have that unit running, no problems at all. We needed 7 gallons of water per minute, and that bucket would have produced 10 gallons of water within 1 minute. So if we would have dumped it out, put it back underneath there, another 30 seconds, we would have been able to fill it back up again. 10 gallons of water a minute, that meant that that well was producing enough water circulating through the coil to provide enough water for a 5-ton unit. So a 5-ton would need 10 gallons of water per minute. And we did not need that much GPM because we're dealing with a 3.5-ton. So therefore we knew we had enough. And like I said, you want to test before and you want to test after, because there should be 0 difference in pressure. There should be 0 difference in gallons per minute. And so this is just an indicator that You know, the hoses on the ground, typically we have sprinklers that are tied into these, and there might be Y connections where we're tying in multiple sprinklers, and we're just irrigating the yard every time that unit comes on. I've had situations to where if the setup is like this, and this is tied to an irrigation, I'm sorry, not irrigation, but if it's tied to a water sprinkler and they turn this off, then no water comes out, then the unit will cut out on a high pressure. So let's go back to that. There are pressure switches here. There's a high pressure switch and a low pressure switch. So in cool mode, you're going to go out on high pressure in the event that you don't have proper water circulation. It's very important for those pressure switches to be there, so you don't want to bypass them, because you could have a problem with a water valve and you don't want that compressor to run that hot gas to get up, and then that compressor short cycle because the pressure switch is bad. Now, or not bad, but tripping the contactor from being energized. So if you take this and you short cycle it, you're going to overheat your compressor, and that damage you can't undo that damage. It winds up being permanent on those windings. The older units will have lockout relays, so if you lost a Y call through a pressure switch, then typically you have to turn the breaker off and back on to reset that lockout relay. Some of the newer models have control boards in them that will do that same very thing that we just talked about. So don't bypass any pressure switches. If the coils are reversed, meaning this one's putting out heat and this one's putting out cool, cool, meaning it's evaporating here, you're condensing up here, so you're getting heat off of it. Then down here, if you don't have water flow, this water jacket will freeze. So all the moisture on the outside of it, plus the water that is inside the jacket, it will freeze because it's not moving. So because it's not moving, it will ice up. That's not good. And so ice is pretty strong, and it can cause damage to the coil. At the end of the day, your low pressure switch is there because it will obviously cut the unit off because of that low pressure. That low pressure and that high pressure switch, it's not just there in case you have, in case you get a freon leak or something like that. You know, that high pressure and that low pressure switch are both there in case water is not moving through this water jacket in cool mode or in heat mode. Those pressure switches are going to capture that on that condenser coil if it's freezing up or it's overheating. And so that's what those pressure switches are for, because water is typically a problem. If we look at all the common problems up here, besides this bottom one, tech doesn't know what he's doing. You know, look here, water, 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 water. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 things up here. And we have 1, 2, 3, 4, 5, 6 things. So 6 out of the 9 things that we have up there, literally 2/3 of your issues is mostly water related. And then about 1/3 of your issues is dirty coils, refrigerant issues, and which is funny, and your technician not knowing what he's looking at. There's not a whole lot more to cover on water to air. It's just looking at the refrigerant circuit and looking at the understanding the layout for the water in and out, and the well pump and the science behind this and what makes it so amazing. And then the rule of thumb of 2 gallons of water per minute per ton. That doesn't matter what the brand is. Your manufacturer may say we only need 1.5 gallons of water per minute. Okay, great. Well, if you have 2, that's even better, right? So you can't never have enough. In the video, we were getting 10 gallons of water a minute. That's fine. You can't have enough, but you can have not enough, right? You can never have enough water. You can have as much water as you want, but there can be a point to where there is not enough water because of something that's going on here. And so I didn't get into any wiring or anything like that, because they pretty much, all that stuff is pretty standard on air to air and water to air. Other than the pressure switches, people think the pressure switches are there for refrigerant values. No, they're there in the event that water is not moving through the condenser coil in cool mode, right? So it will go out on high head pressure, and if the water is not moving through the condenser coil in heat mode, it'll go out on low pressure. That's what those are for, is because, like I said, out of the 9 things, 6 of these things, 2/3 of these things are water related. So water to air unit, remember, most of the time you have a problem, it's water related. And then out of the other 3 things, it can be normal dirty coil or refrigerant issue, or maybe you just don't know what you're looking at. And that's pretty much it. So I want to go ahead and thank you for watching this video again. I hope it helps you out. I know it's a complicated thing out there, seeing these geothermal units and not knowing what to do, because you don't really see them that often. And so when you do see them, it's kind of like a freak of nature. Like, what is that? It's crazy. How is this a packaged unit? And how do you even get in here and work on it? Why is this water going? It's confusing. I get it. But everything's confusing when you don't understand it. So, I'm sure someone else out there that may not understand it either. There's a share button. Go ahead and push it. Send it out to your buddies. Share it. Maybe you're having a service meeting and they're saying, hey, if you have a water to air unit, give it to Jeff over here. Jeff will work on it. Maybe you're going to say, hey, everybody can work on it. Watch this video, right? Like this video by giving it a thumbs up. Support this channel by subscribing. Leave me a comment. I love to read it. Anything that you guys also want to have me talk about, I'm interested in seeing what that is, to see if we can fit it in our agenda. Outside of that, thank you. Stay safe and stay tuned.